Hey everyone, my name is Guanya Shi. I'm a new assistant professor at the Robotics Institute, and I'm starting in the fall of 2023. My research agenda is centered around reliable learning and control for agile robotics. I'm leading the LACAR lab, which is the acronym of Learning and Control for Agile Robotics. And here are some video demonstrations of my research, including agile drone landing, swarm intelligence, fast adaptation of a quadrotor in strong wind conditions, and continuous jumping of a quadruped robot. So one of my research topic is safe learning-based control with learned agility. As we know, deep learning has been incredibly successful in a lot of decision-making problems. For example, deep learning-based method can play a target game much better than humans, master the game of Go, which is a very complicated strategy game, and even solve some real-world dexterous robotics tasks, such as solving Rubik's Cube using just one hand. However, it's unclear whether we can extend this method in real-world safety-critical systems, such as aviation, autonomous driving, and healthcare robotics. In these safety-critical systems, a small mistake or error from the deep learning model could make catastrophic failure. The general idea is to combine control theory and deep learning for best of both. Deep learning offers learned agility and a new capability, thanks to its expressiveness, flexibility, and generalizability. On the other hand, control theory can provide safety guarantees. Here is a recipe. We have some data and a machine learning method. Rather than learning everything from scratch, we will integrate some prior knowledge in the learning process. Such prior knowledge could be some control theoretic constraints from control theory, such as the Lipschitz constant of a deep neural network. Basically, we cannot arbitrarily learn the controller using an arbitrary neural network. The neural network has to satisfy some good properties to ensure the system is safe. Other examples of prior knowledge include some product physics or invariance properties of the underlying robotic systems, such as nominal rigid body dynamics, symmetry, and permutation invariance. And here is a specific example for drone landing. This project is called a neural lander. When a drone is landing, there are very complex aerodynamic interactions between the drone and the ground, called ground effect. This aerodynamic effect is pretty hard to model. So we use deep learning method to model it and used the learned model for controller design. The key here is that we encoded the Lipschitz constraints to the deep learning model to guarantee stability and robustness of the drone. This is very important because we found that if we use standard deep learning method without any constraint, the drone will just crash. Here is a video demonstration where using our method, the drone can smoothly land and track a circle trajectory very close to the ground. The distance between the drone and the ground is within 5 millimeters. Another research topic is offline learning and online adaptation. Many robotic systems have to operate in dynamic environments. For example, drones flying in changing wind conditions, like a robot on complex terrain conditions. So my research goal is to leverage offline data for fast and robust online adaptation. In the offline phase, the goal is to learn an effective representation of different tasks or operation conditions, such that in the online phase, we can efficiently fine-tune or adapt the model in the real time. And here is a particular example called NeuroFly. We use meta-learning to learn a deep neural network representation of drone dynamics in different wind conditions. And then we use adaptive nonlinear control method to rapidly adapt the last layer of the neural network representation. NeuroFly enables fast and robust adaptation in time-variant wind conditions. In this video, a drone is flying in a wind tunnel with fast changing wind speed, and the drone can precisely, safely execute agile maneuvers. Another research topic is structured reinforcement learning and control. The research question I would like to tackle is how to encode control theoretic constraints and prior physics to RL algorithms. So most RL algorithms are general for all decision-making systems, but in many systems, we do have some good inductive bias, which can potentially make reinforcement learning methods much more data efficient, safe, interpretable, and robust. There are two particularly interesting structures. One is superpositional and another is hierarchical. And here is a hierarchical RL and control example for quadruped robot jumping. In this example, the RL policy is giving high-level commands, and a low-level model predictive control policy reacts to RL's command in real time. Compared to end-to-end deep learning approaches, this method is much more efficient and robust. I'm also interested in some other research topics and collaborations, for example, swarm intelligence and robot-robot interaction, building unified theoretical frameworks for learning control theory, human-robot teaming, and reliable perception-based control. Thank you so much.